Hi, welcome back to AP Calculus. This is Unit 7. Unit 7 is all about integrals and integration. We're going to begin our study by looking at estimating the area under a curve using what's called a Riemann sum. Riemann sums are named after the mathematician Bernhard Riemann, who really formalized and made a true understanding of what an integral is. Although, of course, integration and these techniques were first developed by our heroes Leibniz and Newton, it was Riemann who really nailed it down in a concrete, formal sort of way. So he gets to have his name on our calculus work. So let's just dive right into it, shall we? Okay, example 1. Let's say a car is traveling so that its velocity is never decreasing during a 12-second interval. The velocity at various moments in time is listed in the table below. So I have different velocities in different times. What we're going to do is we're going to sketch a possible graph, and we're going to draw rectangles for each one of these situations. So when the time is 0, we're at a velocity of 30 seconds. So we're going to say that this is time here. And this is velocity as a function of time. And so at 0, we'll just say, I'll tell you what, let's count 10, 20, 30, 40, 50. No, we'll count by tens here, okay. So 10, 20, 30, 40, 50, and 60. Okay. Now, at time t equals 0, we're going to be at 30 seconds. We'll be about right there. Then at time t equals 3. Okay, so on the x-axis, I'm going to count. Let's go 3, 6, 9, 12. At t equals 3, we're at 37. So a little bit faster, right? A little faster. That's a 40, by the way, right there. Got kind of smeared. At t equals 6, we're up here at 45. And then at t equals 9, we're at 54. And finally, we're up here at 65 at t equals 12. We want to estimate the displacement of the car during the 12 seconds by finding the areas of 4 rectangles drawn at heights on their left. So what I'm going to do, first of all, is I'm going to copy this so I don't have to redraw it every time. Little sneaky thing, right? Okay, so I'm going to draw rectangles for their height. So what I'm trying to do is get the total distance that this car has traveled. Now, a possible graph shape for this might be something like this, right? And I want to figure out its distance that it traveled from 0 to 12, or more precisely, its displacement. And if I take the left endpoint of each section and use that as my height, I get a pretty good representation of this. Okay, so I'm going to say that if I add up all these rectangle areas, that will be an approximation of the displacement. So the first rectangle has a base of 3 and a height of 30. The second is a base of 3 and a height of 37. The third was also a base of 3 and a height of 45. And then we have a base of 3 and a height of 54. Notice I didn't use the 65 because that was a right endpoint. Now, does it make sense that this would be a displacement? Well, 3 is the change in time, right? That's seconds. And then I'm multiplying it by 30 feet per second. So this unit's seconds times feet over seconds. The seconds will cancel out, leaving me with just feet. You know, we're just assuming that for those 3 seconds, the car was traveling exactly 30 feet per second. 30 feet per second for 3 seconds, that's 90 feet, right? And in fact, I'm just going to use a calculator to throw this in there right quick. Let's see what this would look like. So just so we can get a value. Now, if this was a free response question, and it certainly could, we would just leave our answer like that. Even if it was a calculator portion We don't actually have to evaluate, but we do need to put the units. So the units are an important part of the question. Actually going through and calculating it is not necessary unless it's a multiple choice question. So this is going to be equal to 498, I think that was right, 498 feet. Because the feet and the feet per second reduce down to feet. And if you look at coloring in this image here, these rectangles, then what this ends up being, calculating this displacement, can be called finding an area under the curve of the red line. As you can see, though, it's not a perfect estimate because we definitely have some gaps here that I want to color those in green. So we have some. Why can't I choose that color? There it goes. So yeah, we have some missing places here. So I would say that we probably have underestimated the distance that this vehicle drove. So that's called a left Riemann sum. All right, let's do the same problem, this time with a right Riemann sum. So I'm just going to copy and paste, and I'm going to draw my rectangles with the right endpoint, right? So again, this is the curve that we're talking about, right? Or the possible curve, I should say. But now I'm using these right endpoints. So my first section here actually is above this line, and so is it here, because I'm using these right endpoints to determine which one. Last time I used the left, but because this graph is increasing, last time we got an underestimate. This time it looks like we're going to get an overestimate. Well, let's go ahead and figure out what that would be. I kind of need that table again, though. So 37, 45, 54, and 65. So 3 times 37 plus 3 times 45 plus 3 times 54. And that last one was a 65, I believe. 37, 45, 54, and 65. And they were all widths of 3. And that's going to be in feet. And so what that ends up doing is you might notice that we're going to lose this point here, and we're going to gain this one here. So it ends up being 603 feet. So, pretty big difference here between the two. But you can see my area under the curve estimate this time is overestimating. All right, next let's try a midpoint Riemann sum. Oh, you know what? I said right endpoints here. I mean to say the midpoints. Okay, midpoints. So, you know what? Actually, we're going to change that. We're not going to use 4. Let's just use 1, 2. Let's just do 3. So I'm just going to do 3. So this is a midpoint Riemann sum. So I'm going to make one rectangle here at the midpoint. Then I'm going to go up to here and make another rectangle. Oh, actually, so I'm actually just doing 2. Yeah, so if I'm going to do a midpoint, I really only get 2 of them, not 4. So that's not correct. A little typo. All right. So we'll do 2 midpoint Riemann sums. So that becomes 6 this time times 35 plus 6 times 54. And I wonder what that's going to give us. So that would be 6 times 35 plus 6 times 54, that's 534. So a little bit in between. And I like that one. It kind of, we can see that we overestimate on one side, but we kind of account for that by taking off a little bit on the right. So a midpoint Riemann sum is when you use the height of a rectangle from the middle of each partition. All right, let's take a look at this with a function. And we can look at a little more different ways of doing this because of that. Now that I'll have more data as much as I want. All right, given the function x squared plus 1, estimate the area bounded by the graph and the curve, the graph of the curve and the x-axis from 0 to 2. Okay, we're going to be using a left Riemann sum of 4 subintervals. So I'll say 0, 1, 2, 3, 4. So I'll be counting by a half here. 1.5. So that would be 3 halves, and then this would be a 2. And 1, 2, 3, and 4. All right, well, let's see here. I need to go up a little bit higher. Let's go up to 5. All right, so 0 squared plus 1 is 1. 1 squared plus 1 is 2. 2 squared plus 1 is 5. So this curve is going to be something like this. Okay? And we're going to be estimating the area under this curve. Once again, I'm going to get a quick snapshot of that. And let's start with the left Riemann sum of 4 equal subintervals. So I'm going to have to go from here to here. Then I'll have to get the height at a half, and that's not exactly pleasant, but we can use a calculator or something like that to do that. Or just do it by hand. Then another one, and then my last one will be right here. So you can see, once again, we have an increasing function. We're going to get an area here that's going to be not quite the area under the curve. So my first interval is a length of a half, and so is my second, and my third, and my fourth. So I'm actually going to factor that out and say it's going to be 1/2 times f of 0 plus f of 1/2 plus f of 3/2, excuse me. I forgot f of 1. There we go. And then f of 3/2. So those are 0, 1, 2, 3, 4 different subintervals. And let's see here. F of 0 is 1. F of 1/2 would be 1/4 plus 1 is 5/4. That's not too bad. F of 1 we said was 2, and 3/2 would be 9/4 plus 4/4, which is 13/4. Okay, so let's see. That ends up being, if I put everything over 4, 4/4, 9/4, 17/4, 30/4. And then if I multiply that by a half, it's 15/4. That's our estimation for the area under the curve from 0 to 2 of x squared plus 1. And that's just in square units, but we don't know what that unit is. All right, let's do a right Riemann sum. Okay, so a right Riemann sum of 4 equal subintervals means I have to come up to the curve and go like this. So that's going to be 1/2. And I won't factor out this sign just to show that I don't have to, but I can, times f of 1/2. So I'm going to just plug it in. 1/2 squared plus 1 plus 1/2 times, let's see here, that's 1 squared plus 1 plus 1/2 times, that's 3/2 squared plus 1 plus 1/2 times 2 squared plus 1. And that's a perfectly fine answer on a free response question. We could go ahead and figure it out. I'll go ahead and have the calculator give it to me just because I think it's interesting while we're learning this. So 1/2 squared plus 1 plus 1/2. And you see how we could have factored out the 1/2, right? 1 squared plus 1 is 2. That one's easy to do. 1/2 times 3/2. I want that in parentheses. Squared plus 1 plus 1/2 of 5. We get 5.75. A little different than what we had before, right? Because before we had 3.75. All right, let's do a midpoint Riemann sum with 4 subintervals. Now, this is what I wanted to do last time, but I had to only do 2 subintervals. Forgot about that because I had such limited data. But now we ought to be able to really do this. So what I'm going to have to do is actually find the midpoint of 0.5. Oops, a little high there. Like right there, and then right here, and then right here, and then right here. And you can see how much better that's going to be an approximation, I think. So once again, I'll factor out the 1/2. It'll be 1/2 times f of halfway between 0 and 1/2 is 1/4, plus f of 3/4, plus f of 1 and 1/4. So that's 5/4, plus f of 7/4. Now, unfortunately, this is not accessible in the AP exam, even on a free response. You cannot leave it in terms of f of. You have to go in and write it out. So we'd have to write out 1/4 squared plus 1, plus 3/4 squared plus 1, plus 5/4 squared plus 1, plus 7/4 squared plus 1. Now, one other word of caution, I'm able to factor out this 1/2 only because we're doing equal subintervals. Later on, we'll see that they're not always equal. Sometimes they are different in size, in which case you definitely can't factor it out. You got to write it every time. All right, so let's do that. We got 1/2 times, let's see here, 1/4. Squared plus 1, plus 3/4 squared plus 1, plus 5/4 squared plus 1, and then that last one was 7/4 squared plus 1. 4.625. I think we're starting to kind of get a little bit better approximation. All right, the last one we're going to do is a trapezoidal, my favorite. The trapezoidal Riemann sum is where you make trapezoids out of the sections instead of rectangles. So by that I mean I'm going to have a right trapezoid where the base of the trapezoids, the two bases that are parallel, are actually going up and down. So it's a little unusual. This is the base here going up and down, and this is the other base. And then what we do is we connect them. And so you can see how good an approximation this is because we end up taking the slope of the curve kind of into account. But what's also interesting is it turns out to be just simply averaging the left and right Riemann sum. So the formula for the trapezoidal sum is, 1/2 times base 1, which would be f of 0, plus base 2, which is f of 1/2, times the height, which is also a half. The height going this way, right? And then we have to do that for each one of these. So then plus 1/2 f of 1/2 plus f of 1 times 1/2 plus 1/2 times f of 1 plus f of 3/2 times 1/2 plus 1/2 times f of 3/2 plus f of 2 all times 1/2. Well, if you notice that, I've got every single one of these things twice except for f of 0 and f of 2. And if I factor out this 1/2 out from in front, okay, then the 1/2 for the trapezoids, then what I really got is f of 0 times 1/2 plus f of 1/2 times 1/2 plus f of 1 times 1/2 plus f of 3/2 times 1/2. And that right there is a left Riemann sum. So that's the left sum, right? but I had another f of 1/2, right? I had one here and I had another one here. So I've got an f of 1/2. Again, we can say times 1/2 plus f of 1 times 1/2 plus f of 3/2 times 1/2. And I'll write down here plus f of 2 times 1/2. Well, that's the right Riemann sum. This over here is the right sum. And then we had that 1/2, and we could have factored out the 1/2 of this distance, but we had the 1/2 because of the formula for a trapezoid. Remember, it's 1/2 b1 plus b2 times h. We have that 1/2 times a left Riemann sum and a right Riemann sum. So it turns out this is just an average of the left and right Riemann sum. So it's just averaging, what is that? We said 3.75 plus 5.75 over 2 makes it 4.75, which is really close to our trapezoidal Riemann sum, which we said was a good one. So what did we say it was again? 4.75 is our trapezoidal Riemann sum. So you can either make trapezoids if you have to find a trapezoidal, or you can find a left Riemann sum and a right Riemann sum and average the two. All right, let's take a look at this next one. Water is flowing into I'm having trouble getting it just where I want. Hold on one second. All right, water is flowing into a tank over a 12-hour period. The rate at which water is flowing into the tank at various times is measured, and the results are given in the table below, where R of T is measured in gallons per hour and T is measured in hours. The tank contains 150 gallons of water when T equals 0. Okay, so R of T is the rate at which it's flowing. Estimate the number of gallons of water in the tank at the end of 12 hours by using a left Riemann sum with 3 subintervals. Show the computations that lead to your answer. All right, so I know that at T equals 0, we started with 150 gallons. So I'm going to start with 150 gallons, and I'm just going to simply add how much was flowing into it times the time. If I multiply gallons per hour times hours, I'll have just gallons. So we're using a left Riemann sum of 3 subintervals. So I'll do that one to that one to that one. So I'll have to start on the left. So 8 was the height of the gallons times the change in time, which is 5. Plus on the next one was a height of 8.8 and a change of 3. And the next one was 9.3 and a change of 4. And I'll let you multiply all that out to see what the answer is, because I'm just going to put gallons and call it done. All right, let's do the same one, this time with a right Riemann sum. Well, again, I start with 150 gallons, and then for 5 hours, we're saying we were getting 8.8 gallons per hour because we're using the right endpoint. Plus, then for 3 hours, we got 9.3 gallons per hour. And then for 4 hours, we got 9.2. And that, of course, is in gallons. All right, let's estimate R prime of 3, show the calculations, use proper units, and describe the meaning of our answer. Well, it didn't ask, but the meanings of our answer A and B was that at time T equals 12, there is that many gallons of water in the tank. R prime of 3, since we don't have T equals 3, we'll use the 2 that surround it, and we'll find the average rate of change. So R prime of 3, the derivative at 3 is approximately equal to the secant line, or average rate of change. So 8.8 minus 8 over, and the change in x's was 5 and 0, right? So 5 minus 0. Now this here, the numerator's units are gallons per hour, I think, right? Gallons per hour. So we always put the y units up here, gallons per hour, and then this is a change in hours. So this is gallons per hour per hour. So what that means is that T equals 3 hours, the rate of change in the flow is whatever that is, 0.8 over 5 gallons per hour per hour. The rate of change in the flow is increasing by 8.5 gallons per hour, or the flow of water is increasing. And we could probably say that, and that would probably be better. Let's put it that way. We're going to put it in more everyday language. So the rate of flow is increasing by 0.8 over 5 gallons per hour per hour. Is the rate of flow guaranteed to be 9 gallons per hour on the interval from 0 to 12? Okay. From 0 to 12, is it guaranteed to be 9 gallons per hour? Well, yeah, I would say yes, because of the intermediate value theorem, but we weren't told that this was continuous. So let's just assume that it did. I'll say, assuming R is a continuous function, then by the intermediate value theorem, since R of, let's see here, R of 5 is less than 9, which is less than R of 8, R is equal to 9 at some time between t equals 5 and t equals 8. Is there guaranteed to be a solution of R prime of c equals 0 for c on 5 to 12? Is there guaranteed to be a solution to R prime of c equals 0? I'm going to bring that table down here. Let's see if I can't do that. Well, I can't use Rolle's theorem because I don't have two values that are the same. But I think, as long as R is, and I know it was supposed to say that. I just forgot to say that R is a differentiable function. That's why we knew it was continuous. But I'm going to say that R prime of 3, or actually I'm going to say R prime of t is equal to, what is that, 0.8 over 3 for some time on 0 to 5 by the mean value theorem. We know that, right? And we also know that R prime of t is equal to, let's see here, negative 0.1 over 4 for some time on 8 to 12, also by the mean value theorem. So what we found is there's got to be two different times, one where R prime was positive, the next time where it was negative. And since R prime was differentiable, which the instructions were supposed to say that, we know that it's continuous. So we can say R prime is a continuous function. And so by the IVT, R prime of c equals 0 for some time on the interval from 0 to 12. Hey, and so that's it for our first lesson. Good luck with your assignments.